Hello everyone, I'm Azaria Ahmad from Mechanical Engineering, Bandung Institute of Technology. Here I will explain you about my experiment, simple steam power plant experiment for basic phenomenon on mechanical engineering project. First, we'll talk about steam power plant. Steam power plant use water as its working food. It's closed loop system, and the water will be boiled at the boiler and will flow to the turbine, and the turbine will convert with the generator to electricity, and it will be condensed and will be pumped to the boiler again. So it's a closed loop system. But in this experiment, I will use open loop system. I will only use the boiler and the turbine and generator. Um, Something like this for the schematic, experiment schematic. I use kettle as boiler and micro hydro turbine for the turbine. In there, will be talk about energy conversion phenomenon and vapor dome phenomenon. How about the principle? First, the boiler will boil the water and the water becomes steam. In here, will be there is a data acquisition. The pressure and the temperature will be measured for the steam before the turbine, and then the steam will flow to turbine, and the turbine will be converted to electricity, right? We will measure the voltage and the ampere, the current, and then it will flow to the outlet, and we'll find the velocity for the mass rate. There's an assumption that there is no heat loss at pipe, no pressure loss, and it is steady state. Here the 3G model for the experiment. I use kettle, and there is pressure gauge, there is a thermocouple, RAXC100, and there is also valve and here the turbine, the micro hydro turbine. Here the model, and here the schematic for the in the slide before, just a rock plan, and here the schematic, the boiler, and there is pressure gauge, there's a thermocouple, there's a turbine. The turbine will be measure uh, the the current and the voltage will be measured, and there is resistance here. I use lamp as a resistance, and the anemometer will be outlet to measure the velocity. Okay, here the exploded view of my TG model. There's RKC control PID, there is a pressure gauge, punch bar, and there's connector, there's turbine, there's valve, etc. And here the flow chart, first to boil the turbine and etc. I will explain it in the video, but for this stage is a calculation. First we will calculate the environmental pressure. I use isothermal in here, and we find the power, V multiplied by I multiplied by current, and there is also mass rate, there is rho, the density multiplied by velocity, and there is if if flowchart. Is there is all the data can be collected? If yes, we just use this um, this equation, such as enthalpy at outlet is enthalpy inlet minus V dot per m dot. And if not, we assume that the turbine is isentropic. So we can calculate the enthalpy at outlet with the pressure at outlet and the entropy at outlet. Then we just find the X, the quantity of steam for Vapor phenomenon, and we analyze, and it's the end. So maybe it's the flowchart video for the left one. First, we will open the kettle, right, and fill it with water. After it filled with water, it just boil water until it's become steam, and the steam will flow through this to the pressure gauge and to the thermocouple. And then the turbine will be to the turbine and to the valve. The valve is closed first, then will be open and just measure the anemometer at here, something like that. Why the valve is closed? The valve is closed to increase the pressure and also to make the vapor is high enough to flow to the turbine. And here the experiment tool, the right one is the monitor rooms, I think, and the left one is the experimental room. I use to device it here, external camera that I use it here, and my mobile phone, and it's connected to the Zoom, so I can monitor its real time. I so I yeah, something like that one. And here the video is the flow of steam, and it's also recorded. For the recorded one is in the next slide. Here the experimental video, the zoom, it's sorry, speed speed to multiply by 2, and after it close, the voltage is increase first because the steam will be flow. Then I open it, and it will increase to, I think, until 39, 38, 39 millivolt. Then after sometimes, wait minutes, maybe 1 minute again, multiply by 8, it will decrease. Okay, we'll discuss that later. And here experiment video, I can't measure the flow rate because it can be detected by anemometer. So we will use isentropic turbine assumption. It's only 0.0 meter per second. So yeah, something like that lah. And here the result, the voltage initially steady at 13 millivolt. Oh yeah, this is the temperature and this is the voltage. And when the valve is closed, it will high until 39 millivolt. But it decrease and up again and decrease again until 30 millivolt again. Why there is low voltage here, but it will become high again? I think it's due an inaccurate tools, the measurement tool, or non-constant steam generation, or it also can be constant steam. I'm sorry. I think it's also can be due to non-constant steam loss. Steam loss. I'm sorry. Okay. Next. Here the outlet pressure measurement that I find that it's 0.989 bar. I use isothermal assumption with gravitational acceleration constant by length on NOS to 20 and 20. And here the thermodynamics from last slide, we have different operator 90, 98, 99, and 100. But for 98 and 99, it's lower than outlet. That means it's not possible because the air, the gas is flow through to the lower pressure. So I will use 100 Celsius for the analysis. Actually, uh, this can be calibrated, but I will not use that because it's too hard. And here the thermodynamic calculation, I use extreme. Here the extreme, and here the formula. I use extreme 2.6, I think, and here the result. By extreme, I can find the X at outlet instantly. So there's an additional analysis that not be is not for the conversion, but based on readability of the tool, it can be concluded that the current generated is less than 1 milliampere. And for its speed, I think cannot be concluded because the anemometer cannot be rotated. So I use ampere meter as the base for the analysis. Then we find the mass rate, the maximum mass rate, if the maximum current is 1 milliampere, something like that. And for the velocity, it just found that 1.6 the power of -5. It's too small. Okay. So yeah, I think it's possible why the anemometer can read it because it's too small. And for the conversion, the power increase with the increasing of mass rate. After the valve is opened again, the voltage is increased from 30 millivolt to 39 millivolt. And the power dump phenomenon can be observed, and the steam quality at the outlet based on calculation is 0.909986511. Okay, for the suggestion, it's necessary to ensure that there is no steam leakage at the system. So the steam can be flowing perfectly in the system, and use the boiler with large high Q input, and use more accurate tool and use steam or gas turbine instead of water turbine. And thank you.